Hello students, in the previous class we have seen the RNAs equations, and at the end of lectures we have seen the evaluation of energy of activations of any reactant molecules, and in that case we have discussed the first methods which is used to determine the activation energy of reactant molecules. Dear students, today I am going to discuss the next and second method for the evaluation of activation energy. That is, the second method is what? Sorry, second method is graphical method. Second method is graphical method. In the first method, the name of first method is what? Integrations method. By using integrations, we can calculate the energy of activations of any reactant molecules. So, by using graphical methods, we can also calculate the determine the activation energy of reactant molecules. So, how we can calculate the graphical energy of activations by using these graphical methods. So we will discuss these graphical methods. Dear students, as we know that what we know that RNAs equations. We know that RNAs equations we have already covered. So we know the RNAs equations. So RNAs equation is what? dlnk upon dt is equal to EA. EA means what? Energy of activation of reactant molecules, and RT square. This is the RNAs equations we have already seen in our previous video lecture. So this is the equations we have you note down in your notebook. So this is the RNAs equations. So I can rearrange these equations and integrate these equations like, so I can rearrange these equations. I can write rearrange the equations. One, as I can rearrange this equation as dlnk is equal to energy of activations upon R and into dt upon t square. dt upon t square. Then this equation number second. Then I can integrate. So I can write like that: integrate the equation second. Integrate the equation second as. So integrations like that, dlnk is equal to E as it is, because the activation energy we have to calculate or we have to evaluate the activation energy of reactant. R is the molar gas constant. So integrations of dt upon t square. dt upon t square. This integrations is without limits. So when I solve the without limit integrations, so I can write like that: dlnk, what is left here? lnk is equal to EA as it is, R as it is, because this activation energy we will have to evaluate, and R is the molar gas constant, and after that minus 1 upon T plus ln of plus C. This is the integrations constant, because we are integrating these equations without limit. If suppose I am writing with limit, then I cannot write this constant. This is integrations constant. This is C is what? Integration constants. Okay, so these equations I can write like this: ln k is equal to EA upon RT as it is plus C. C is what? Integration constant. So suppose C is equal to ln of A. C is equal to ln of A. That is, we can write where A is called Arrhenius constant. Arrhenius constants, because we are dealing with the Arrhenius equations, so we can say this C is ln of A, and where A is called Arrhenius constant, so I can write like these equations. I can write like that: ln of K is equal to minus EA upon RT plus ln A plus ln A. If I want to plot a graph, so I can see this equation is just like that: y is equal to mx plus c. Y is equal to mx plus c. Of course, here is negative sign, so the graph will come will be decreasing order, and x is y. On the x-axis, your temperature is there, and on the y-axis, ln of k is there. Ln of k is there. Okay, so if suppose I can suppose I plot the equation, this graph like that. If suppose I plot the graph, ln of k on y-axis, this is your y-axis, this is your x-axis, this is your x-axis. On the x-axis, what? 1 upon t. 1 upon t is here, 1 upon t is here. Because of this negative sign, the plot may be like that. The plot may be like that. So this is on the y-axis, this is your intercept, and in value of intercept is what? The value of intercept is what? ln of A. ln of A. That means Arrhenius constant. You can find out this ln of A. And slope value. Here is your slope. So the slope value is what? Minus EA upon R. Minus EA upon R. So on the basis of this slope value, if suppose I have find out the slope value. After find out the slope value, I can calculate the R value. R is what? Molar gas constant. So we have to we know the value of this R. We know the value of this slope. So I wanted to calculate the activation energy. So I can calculate like that. So therefore, EA is equal to minus slope into R. Minus slope into R. So on this graphical method, I can calculate the activation energy of the any reactant molecules. Like that, plot the graph like that, and if I am plotting the graph, if I solve this, I will determine the R value. R value is what? Molar gas constant. Determine the slope value, and by using this equation, I can calculate the activation energy of reactant molecules. Okay, so this is the graphical methods. So this is the equations we can calculate by this equations. I can calculate the activation energy from the graph also. So these equations I can write in another form also, because ln is there. So we know the ln of k, that means there is what? Log to the base e. So I can write these equations. I can this equation number 3. So in this equation number 3, I can write like that also: log of k. If I am changing the log to the base 10, so I can write like that: log of k is equal to minus EA upon 2.303 R T plus log of A. Log of A. Like that, like this graph, I can plot another graph like that also. Nature of graph is say. Nature of graph is say 1 upon t on x-axis, on y-axis log of k, and the nature of graph is like that. Here is your intercept. The value of intercept is what? Intercept is equal to log of A. Log of A 303 into R. If I wanted to calculate the activation energy, then I know the value of flow. The value of 2.303 multiplied by R. The value of R we have to know. We know the value of R, so we can calculate by using these equations. EA is equal to minus 2.303 into R into slope. So like that I can calculate the what activation energy of any reactant molecules. So this is all these things about the RNA's equations. We have seen the RNA's equations, and after that we have seen the how to calculate the activation energy by using integrations methods and by using graphical methods. So all these things I hope you may understand and note down in your notebook. Okay, so dear students, up to this we have covered number of things and number of mathematicals is there and number of terms and concepts is there in the chemical kinetics, and we have discussed all the things and note down in your notebook all the things. So up to this we have covered what zero order reaction, zero order reactions. So for the zero order reactions we have discussed the integrated rate equations, and the video lectures will be available for you. So for the zero order reactions we have covered, and for this we have for this zero order reactions the integrated rate equations we have covered like that: K upon T plus C naught. This is the integrated rate equations for the zero order reactions, and for this we have write down the zero order reaction half-life period for the zero order reactions, and for zero order reactions we have write like that: zero order reactions is directly proportional to the initial concentrations and inversely proportional to the rate constant of zero order reactions. K naught is K0 means what? Here is your K is for what? Zero order reactions. So this is the integrated equations. This is the integrated rate equations. And this is the half-life period. So you have to remember half-life period. You have to remember all these things, because on this basis we can calculate the number of numerical problems, and so you have to remember these integrated rate equations for zero order reactions and half-life period for zero order reactions. Like that we have covered second thing, that is first order reactions. And for first order reactions we have discussed the integrated equations like that: ln of Ct minus ln of C naught. Ln of Ct minus ln of C naught is equal to minus Kt. Or another form of these equations we have covered: K1 is equal to 2.303. Another form 2.303 upon T log of C naught upon Ct. This is the logarithm form to log to the base 10. This is the log to the base e. These two forms we have already covered in our video lectures, and for this first order reaction we have covered T1 half is equal to 0.693 into upon K. This is for zero order reactions for the what, or half-life period for the what, first order reactions. These equations or these derivations we have covered. Another equal initial concentrations unequal initial concentration. This K2 is equal to 2.303 T into B minus A log B into A minus X upon A into B minus X. This is the integrated rate equations when the two reactant molecule having unequal initial concentration. This is for what? The reactant molecule have equal initial concentration. This is for first order reactions. So this for second order reactions half life period equations we have covered. So T1 half is equal to 1 upon C naught into K. This is for what? Second order reactions. Half life period is inversely proportional to the initial concentrations. Here is directly proportional to the initial concentration. In this first order equations, first order integrated equation or first order reactions, half life period of reactions is not depend on the what initial concentration. In this equation half life period is directly proportional, in this inversely proportional, but here inversely proportional, not directly proportional and not inversely proportional. That means the half life period of first order reactions is independent on the initial concentrations. Okay, so up to this we have covered, and finally we have covered. I'm writing like this. I'm writing here RNAS equations. We have just covered RNAS equations. RNAS equations. RNAS equations, and these equations is we will use, or we will calculate the energy of activations. The RNAS equation is like that: dlnk upon dt is equal to EA upon RE square. So we can calculate by using these equations the energy of activations. And integration methods we have covered, and by using these integration methods we will calculate the energy of activations. Graphical method is there. So all these things is related to the chemical kinetics, and all the chemical kinetics topics included in our syllabus I have covered. So all these things you have noted down in your notebook. And most important thing is that integrations, you may be asked derivations for the zero order reactions, you may be asked derivations for the first order reactions, for the second order reactions we can, or some half life period of zero or first or second order reactions. All these things you may be asked in your question paper, so you have to prepare all of things in your notebook. Okay, so on this basis we will solve the number of numerical problems in next video lectures. But you have to remember all these things, or make a chart of these things in your notebook, or by using that chart we can calculate, or we can determine the how to calculate the rate constant value, how to calculate the half life period. So the number of problems we will solve in our previous lecture, or in our next lecture. Okay, so I hope all these things